Now we're going to be looking at another function operation called composition. Let's think about this scenario. You have a coupon for $10 off your favorite store. You decide to buy a shirt that costs $20, but it's also on a discount of 20% off. So let's look at the two ways we could do this. We can do $20 minus the $10, which will leave me with 10, and then we can do the 20% off. Well, 20% of 10 is 2. So that leaves me with paying $8. Now if we do it the other way around, so let's take 20% off first. Well, 20% of 20 is 4. And then let's take off the coupon. I'm going to end up paying $6. So obviously you would want to go this route because $6 is less than 8. But the computer at the store is always going to do the best for the store, which means it's going to do the coupon and then take the discount of 20% off. Now this idea of having two different functions going on, the function of subtracting 10 and the function of taking off 20%, is called composite functions. The idea of composing functions is really just taking one function and plugging it into the other function everywhere I see the variable x. Now the way we would pronounce this notation, we can say g of f of x, or we can say g is composed of f of x. So we can do it two different ways. We can plug in f of x into g, which means I take the function f of x. Everywhere I see an x in g, I'm going to put what f of x is equal to, and then I'm going to simplify. Now the other way around is exactly the same thing, except for I'm going to take g of x, so whatever the function might be, and everywhere I see an x and f, I'm going to plug it in, and then I'm going to evaluate and simplify. When we compose two functions, the domain is always the x values of the first function, for which our range is equal to the domain of our second function. So we have f. We plug in values for f, and that gives us our range. Well, the range of f must be equal to the domain of g. So we can't have values that work in f but are not going to work in g. So everything has to be workable for both functions. When we looked at adding and multiplying functions together, we saw that the order does not matter. Addition and multiplication are commutative, so the order in which I do them doesn't affect my result. Now when I subtract or divide functions, the order does matter. So whichever one I do first will give me a different answer in some cases. So it's good to ask ourselves, when we compose two functions in different orders, will we get the same answer? When I do g of f of x, will I get the same as when I do f of g of x? Now think about the order in which you put on your socks and shoes. Does that matter? Well, you should always put your socks and then your shoes. If you do it the other way around, you might get some funny looks. So that means when we do composite functions, when we compose two functions together, we may not always get the same answer when we change the order. Now I'm not saying they won't ever be equal, but they will not always be equal. So composing two functions is not commutative. We cannot assume that they will always be equal. Before we begin this example, I want to look at a little side note. So let's say I asked you to find g of 5. Well, you would know that would mean I want you to take 5 and put it in the place of x into the function of g. So everywhere you see x, you would put a 5. So for this particular problem, you would put 5 where you see an x, so we would get 5 squared, and g of 5 would be equal to 25. Now we're going to be doing the exact same thing when we do g of f of x. Everywhere we see an x in g, we're going to put the function f of x, which is x minus 5. So f of x is x minus 5, so g of x minus 5, and I'm going to replace x with x minus 5, making sure to put my parentheses here. Now we all know that that means that's x minus 5 times x minus 5. which is a perfect square trinomial. So we would end up squaring the first term, multiplying these together and doubling it, and then squaring the last term. So g of f of x would be equal to this function x squared minus 10x plus 25, which would be a parabola, right? If we tried to graph it, a quadratic function. Now we're going to look at if we want to find g of f of negative 3. So what that means is I'm going to look at my composite function, g of f of x. Everywhere I see an x, I'm going to put in a negative 3. So I'm going to plug in negative 3, and then I'm going to evaluate. So evaluating that, we're going to get 64. So now we're going to do f of g of x. So everywhere I see an x and f, I'm going to plug in what g of x equals. So that's the same as saying f of x cubed. So everywhere I see an x and f, I'm going to put x cubed. So that's 3x cubed minus 2. Well, when I simplify that, that's just 3 times x cubed minus 2. So f of g of x is equal to this cubic function, 3 times x cubed minus 2. So now evaluating that at 2, I'm going to plug in 2 everywhere I see an x. Well, doing my exponent first, I know 2 cubed is 8. Now I'm going to do 3 times 8, which is 24, minus 2, which is 22. Now give it a try and make sure you put your work and your answers in your notes.